now we get to a few more interesting solids of revolution. And this one says, find the volume of the solid formed when the shaded region is rotated around the x-axis. Okay, so we have, this is the axis we're rotating around. And what I'm trying to do is take this shape and rotate it around this axis. Okay. And let me see, this is going to be a little bit harder for me to draw, but let me use, let me have this green represent the outside, and let me let, let's let blue represent the inside. So what we have here is this. I will have, it's not quite going to be hollow, well, it'll be hollow. It won't have a hole all the way through it, but it will, that's kind of bad. Let me try that again. But it will have this hole that goes all the way, this dimple that goes all the way to the other end. So, this right here is part of it. Okay. And so what we have is, let me do this, is we'll have this sort of shape. Okay, so that's the inside. This is going to give me the hole that we have. And then the outside is going to be based on this parabola. So the outside shape is going to look like this. And let me see if I can make this look really kind of nice. So, and this one, okay. Alright, so this is the basic shape, and the area between these two curves is what I'm looking for. There's this blue thing is actually a hole that, or a sort of dimple running into it. And here's the idea, okay? If I were to, and I'm going to use the washer method, it's like the disc method. If I were to take a cut out of this, okay? So any sort of cut right here. Okay, that's really close enough. Okay, if I were to take this cut, what would happen is I would see a large circle on the outside defined by the green function, and I would have a slightly smaller circle on the inside defined by the blue function, and I want to find this area between the two curves. And here's what we need to notice. This inside function will have one radius, we'll call it R1. This outside function will have a different radius, or this outside circle will have a different radius, R2. And R2 has to be bigger than R1 for our formula to work. And the area of this shape, in terms of R1 and R2, will be equal to pi multiplied by R2 squared. R2 is the bigger one here. R2 R2 squared minus R1 squared. And basically it's the circle, outer circle area taking away the inner circle area. Okay. The two radii. Alright, let's look at this. So blue, the R1 in this case is this line 2x. So R1 is going to equal 2x for any x value. So for any cut I can make through this at any x value, that's what R1 will be. My R2, my outside R, will be based on this parabola. So R2 is equal to negative x squared plus 4x. So that's my outside function here. Okay. And so the idea here now is that I have R1 and R2 in terms of x, both. And I have them in terms of x because the areas will be changing as I'm either closer to 0 or moving farther away. The areas of the cross-section will change. So we need to figure out the volume, and the volumes are going to be equal to integral from start. Let me put A and B. We'll talk about which one's there. From start to stop of the areas with respect to x in this case, because we're going across this way. Now, the area, well, we know this right here, and so that gives me that the area in terms of x will just equal pi multiplied by R2 is negative x squared plus 4x, the outside function, squared. R1 is 2x, so minus 2x squared. And that'll be the area of any one of my cross sections, these little washers. And so I know that the volume will equal the integral. And now let's talk about this. We can see that they meet here at 0, 0. So basically I'm trying to figure out where these two intersections are. That's going to tell me. So that's where the two functions meet. So I want to make both of these equal to each other. So I want to find out where 2x is equal to negative x squared plus 4x. Do a little bit of solving on this. I get, I'm going to move the x squared over here and move the 4x over here. So I get x squared minus 2x equals 0. I factor out an x. I get x times x minus 2 equals 0. And I get that x is equal to 0. That's right here. Or 2, and that's right here. And since I'm going across dx's here, I'm going to use those as my endpoints. So from 0 to 2 of my area, which is pi times negative x squared plus 4x squared minus 2x squared dx. And I usually, when I have this in a formula, I usually have the pi out in the front, so it's a constant multiple, doesn't make a difference, but let me rewrite that because that's the way we usually saw it in class. So pi multiplied by the integral from 0 to 2 of, I'm not going to bother even, well, no, I'll just leave it like that. So negative x squared plus 4x squared minus 2x squared dx. And let's jump to the calculator. Turn it on. Make sure it's working. Okay, so we have pi times math 9, which is the fn int, of, all right, here we go, negative x squared plus 4x, negative x squared plus 4x, close that off, squared, minus the inside function, 2x squared. As we go so dx as we go from 0 to 2. Let me double check, make sure this is all right. So my outside function, negative x squared plus 4x squared. My inside function, 2x, as x goes from 0 to 2. Close that off, and we get approximately 20.106. So let me put that in. So that's approximately 20.106. Final answer.